me? Is it too loud? Too loud? Okay. Is it okay? Okay. Yeah, today you'll be kept awake. Okay, welcome to this 5th lecture of Smart City Lectures. We will take a break from the previous thread of lectures and have a standalone here called Introduction to Encryption. So it doesn't matter if you've viewed or not the previous 4 lectures. The idea here is that encryption is so an important topic when you work with creating information systems. And it's one of the topics most shunned for some reason by engineers. If you look at how information systems are being built, most engineers shun this topic. They feel perhaps not qualified or to work with this. And so the idea of this lecture is to give a brief overview. We will fly over the encryption land, so to say, and show it's not terribly complicated. And if you understand the basic principles, you will be able to navigate and help make your solutions, if not secure, at least more secure or less vulnerable. You might have heard of these names, protagonists in encryption. You have Alice and Bob, most famous of all protagonists. And you have the evil Eve. For some reason, Eve is always the evil one. But Alice A wants to send a message to B. How can that be done without Eve finding out? So this is the basic problem we want to study. And obviously cryptography means, it comes from the Greek word hidden and writing. And how do you write so that no one else can read? And it's a very old branch of mathematics or technology, how you want to look at it. And for thousands of years we have used what's called substitution ciphers. You might be familiar with those. If you've watched any movies from the Second World War, you have seen the Enigma machine, which is an example of polyalphabetic cipher, where you basically swap one character for another in a systematic fashion. The problem of cryptography was solved in the 1800s. You can say there is only one method that is cryptographically secure. It's proven to be secure. And it's called a one-time pad. The problem obviously is to keep the key secure also. So one-time pad means that you have any message and then you XOR, for instance, a random number of bytes or number of values on top, and the result is cryptographically secure, which means that if you have Eve coming in, finds any random bytes and is able to get a message out of it, that message is equally probable as any other message of the same size. So there is no way to know if that's the original message. Now, to get this to work, previously you used code books. You created long books of random numbers. Obviously the sender and the receiver had to have the same book, and you could only use the book once. And obviously the problem was not breaking the cipher, it was getting the book. So it might not have been very efficient. So today we use computerized methods obviously, and they are very similar to the one-time pad, many of them. So we try to create mathematical models to create random numbers in a series, or pseudo-random numbers as they are called. For instance, there are other problems. We have a series of problems that are easy You have functions that are easy to compute, but very difficult to reverse, for instance, such as the integer factorization you might have heard. So if you multiply two integers, that's easy, but if you have a large number, to find the integers of which it consists, its factors, is difficult. The discrete logarithm problem, we'll talk more about that also, and an elliptic curve discrete logarithm problem are examples of mathematical problems used for cryptography. For now, it might be good to just make a division. We have different types of methods that we call symmetrical, and others that are called asymmetrical, and they have vastly different properties, and we use them differently. So symmetrical means we use the same code or secret or key both for encryption as for decryption. Asymmetrical means we have two keys, one for encryption, one for decryption. And we'll talk about the different properties of these. Cryptography is not only about encrypting. We talk basically about these 6 different types of functions that we do with cryptography. The first, random number generators, or pseudo-random number generators. We use them in statistics, etc. We use them in cryptography. We talk about hash functions. You most surely have heard about hash functions. Then obviously we have encryption and decryption, but last but not least is how do we sign? We can sign messages so that the receiver knows who sent them. And then we have the problem of key distribution. So these 6 problems we have to know more about to understand cryptography. Random numbers. So any programmer has used a random number generator. In cryptography, we have to know how good a random number generator is. And perhaps if we don't know so much, we at least have to select one that looks good. The reason we want to have a good random number generator is obviously for the one-time pad problem. The better random numbers we can generate, the more secure we can encrypt the data. And the other way around, if we choose a bad random number generator, we create vulnerabilities that others can exploit. We also use random number generators, obviously, in our simulation and statistical applications. But without delving too deep into the algorithms of random number generators, typically a computer has some kind of cryptographic library that provides this for you. And there are differences between software and hardware generated random numbers. If you use a modern programming language, the random numbers are typically okay. The main difference between hardware number generators is the amount of random numbers they can generate. So it's typically 20 times more efficient in generating random numbers. There are services on the internet you can use to validate how good your random numbers are. And how do you validate a random number generator? So what you do is, or what they do, they create statistical models or probabilistic games, you can say. And they assume if the random numbers are truly random, it will create a certain kind of output. And so they play the game with very many random numbers that you generate, and they compare the result. So if you go into this link, for instance, in Austria, CIZ in Austria, you can upload random numbers, and it will tell you how your random number generator ranks with others. And there are a lot of random number generators, both available in your software packages, but also standalone. So if you really need a good random number generator, there are commercial random number generators that are better than others. There are also commercial that are poorer than the free ones. but at least there you can know. Hash functions, you might have heard of. Hash in English means to cut something into very fine pieces and mix them together into something unrecognizable. And that's basically what a hash function does. It takes a long message, hacks it up into very many small pieces, mixes it up in a sense, and creates what's called a digest. And this digest has to have certain properties. It's a fixed length digest. The message can be variable length, but the hash is fixed length. And it's supposed to be unstable in the sense that a small change in the input message will create a very big change in the output. It's also deterministic, so the same message always produces the same digest. And it should be very difficult to invert. They say it's not invertible, but that's perhaps not correct. But it should be difficult to invert the hash function. Hash functions are used in very many applications. It's used to create random numbers, obviously. So you can use a hash function repeatedly on itself, and it will generate pseudo-random numbers. We can use it to sign messages. So if we have a message and we use a hash function on it, it creates a digest that's unique, more or less, to the message. And so we use this hash function to sign that, show that we are the senders by providing a secret in it, in the message. We can use it to manage passwords more securely. I'm sure you've read thousands of articles about passwords getting hacked in sites because they store the passwords in the databases. You could store the hash of the password instead, or hash of the password and the salt. And then when you compare the password, you compute the hash and compare the hashes instead. So if someone hacks your database, all they get are hashes and not the actual passwords. And by introducing what's called the salt, unique value, the hashes are different in different installations. You can use it in authentication. You can use it in proof of work. Blockchain you have heard of. So proof of work means that you have to add some random number to your message until the hash has sufficiently many zeros in it, for instance. It's very difficult to find the salt you need to create a certain hash. So by stating that you have to have a hash with so many zeros, you have to randomly try very many salt values. And so it consumes a lot of energy and computing power, and that's considered proof of work. It's not easy to do. You can also do it in authentication mechanisms, saying that when you log into a site, you have to compute 1 million hash values of your password. So to put load on the client, so you cannot spam the server, for instance. You've probably heard about these hash functions. These are the most commonly referred to. The MD series of hash functions are obsolete. They're still being used in many applications. If you see them used, you should suggest they change them. You have the first SHA hash function, which is also considered obsolete since Google created a collision on it not so long ago. And you have a second and the third generation hash function. And the third generation is also quantum secure in a sense. And when you compare different hash functions, you will see, if you look at, for instance, NIST reports or other big agencies providing calculating the security level of different algorithms, they provide these tables, and it might be good to learn to read them. So for instance, if you have these different hash algorithms, you might notice that they have different digest lengths. And typically, the longer the digest, the more difficult it is to break it. It's not always the case, but typically. They calculate what's called a collision bits. And collision bits means how many, you could say, how many bits of entropy is there? If you take 2 to the power of this value, that's the number of times you have to randomly create 2 messages according to some algorithm, and they will have the same hash value, for instance. And so this corresponds to what we'll talk about later, security level. When we design applications and information processing, we have to decide what security level we want to maintain. We don't just select an algorithm. We select first the security level we want to maintain, and then select algorithms that suit us to match that security level. As you see, the third level of SHA also have a quantum collision estimated. So they assume we will reach a point in time where quantum computers become available, and so it's important to have cryptographic methods that resist quantum computing algorithms. You will see here also something called a length extension. Some hash algorithms have a larger internal buffer than the digest. Others have the same size internal buffer as the digest. Now, if you have a same size internal buffer, executing the algorithm on its own result becomes deterministic. So if you are listening in and you find the hash value in the middle, you can compute the rest because you don't have to guess what's in the internal buffer. Typically, you can compute hashes in sequence on blocks of data. And so these earlier algorithms, they have no such added bits in the internal buffer, so they're vulnerable. And so you have to use another algorithm to make these more secure. We'll talk about these algorithms. But the more modern algorithms, they have larger internal buffers, so they become less vulnerable, more random, so you can say. You don't have to memorize these values. It's just for you to know that if you have to compare, you can watch these tables and understand what they mean more or less. So HMAC, message authentication, or hashed message authentication codes. So the point here is to solve the length extension vulnerability when you compute the hash on results of earlier hash computations. And so we don't have to go into the formula as such, but the point of HMAC is to know what it is, because you will see it. If you read any type of security or cryptography literature or standards references, you will find this HMAC everywhere. And it might be good to know that the point of the HMAC is to make less secure hash functions more secure. And so instead of computing the hash on the actual message, you pad it in certain ways so that this length vulnerability is removed. It uses a secret key. And so if we look at the security level or security strength of these functions, we can see that while the SHA-1 is considered obsolete by itself, together with HMAC, you still have a 128-bit security strength for that hash. So it improves security. If during the lecture I'm talking too much Greek, you want to ask any questions, please feel free to to raise your hand, and we have a microphone here. It's recorded, so be nice and polite. In Greek, yeah. We take only questions in Greek. Symmetric ciphers. Remember, ciphers use the same key when you encrypt as when you decrypt. So the basic properties of the most common symmetric ciphers are that they are very fast. So it's an inconvenience to have the same key both for encryption and decryption, because you have a problem of key distribution. But they're very fast. And so if you want to encrypt a lot of data, you want to use a symmetric cipher for that. You have two types of symmetric ciphers that are common. You have block ciphers. Block ciphers meaning that they encrypt or decrypt, they work on blocks of fixed size. You have stream ciphers that work byte per byte or bit per bit in a stream. And typically, by design, you could say, when these algorithms are designed, they aim at having a security level equal to the key size. And over time, this decreases, obviously, because mathematicians and security experts, they find vulnerabilities. But by design, the security level is the same as the key size. That's rule of thumb. The most known cipher, Advanced Encryption Standard, AES, is a symmetric cipher, and it's a block cipher. We all have to know. Anyone working with encryption should know AES. When you configure a block cipher, you don't only have to know the key to use. You have to know how to handle consecutive blocks. And you have to know how to pad blocks if you don't have enough to fill the block. And you have to know what's called an initiation vector or initiation values. These parameters you have to know. If you don't know one of these values, your encryption or decryption will fail. And you might wonder why. Now, the easiest, the simplest way to handle consecutive blocks is called electronic codebook. It's completely worthless, obviously, but it's available in most libraries just to show how worthless it is. So what you do is you take a plain text, that's the unencrypted message. You encrypt it with your key and you get the ciphertext. You do the same for all blocks in the message. Now obviously if you have an image and you encrypt it like that, you still see the image because our brain sees the patterns. So you have actually not encrypted, you have just distorted the image somewhat. So electronic codebook is vulnerable to a lot of attacks, obviously. It's like a big substitution cipher, you could say. So what you have to do is you have to find an algorithm to join adjacent blocks. And one which is common is called cipher block chaining. What it means is that you have your unencrypted text, you XOR it with the initiation vector. You don't have to do this. This is what the hardware does for you, but the initiation vector is XORed, then encrypted with a key, and you get the encrypted block, but that encrypted block is used as the initiation vector of the next block, and so on. So you have connected a chain of blocks. And so you cannot see any pattern, for instance, at least visually. But there are other types of block chaining, like the cipher feedback, similar, but you encrypt the initiation vector and XOR the plain text after. You connect it like this. typically in a library, these are just enumeration. You have to choose one method. If you choose one method and the other side chooses another method, obviously you cannot communicate. You have to choose the same method on both ends. Output feedback is another method. There are just slight variations. Counter is interesting. This is often used, and I include it here to show that the initiation vector doesn't have to be secret. It doesn't change the security level of the algorithm. Only the key has to be secret. So here you use a deterministic initiation vector, which it might have a nonce, a unique small part, but then it has a counter 0, 1, 2. The only important thing here is that each entry is unique to avoid this problem with finding patterns. So the initiation vector and the pattern is typically publicly available. It's not considered a secret. If you look at the common symmetric ciphers available in just standard frameworks, I would say the AES, the Advanced Encryption Standard, is the only one that still that is not obsolete. Most other older methods are too weak or vulnerable. And as you can see, the security level of the 128, 192, and 256-bit sizes are more or less the same as the key size. They found some theoretical vulnerabilities, but they don't affect really the security level in any practical sense. That's good for you to know. Only one algorithm to learn. So only one. So just a minute. There seems to be a noise here. So we usually have visitors here from outer space coming. They say it's a ventilation. Now it was some. Okay. Well, let's continue. Thanks. If you're perversely interested in this algorithm, you find it in this Federal Information Processing Standard, where it's described. But what you need to know is that the keys are different sizes, but the block size is always 128-bit, and therefore the initiation vector also 128-bit. And depending on the security level of your application, you set it up accordingly. So important here, don't just choose the most secure because you believe that will make your application more secure. Because if you combine AES 256 with some other method somewhere else, which is poor, then the security level is the level of the poorest algorithm. So take care to select one security level and then have a use it consistently throughout the architecture. Now, so if symmetrical ciphers are so efficient and fast, why do we need asymmetrical ciphers? And asymmetrical ciphers, they're much slower, but they help us solve the key distribution problem. So typically you have heard about public key cryptography, public key infrastructure, and such things. These are all examples of asymmetrical ciphers, where you have a public key which you can distribute to anyone, and a private key that only you have, and you never have to distribute it. The public key, since you can send it to anyone can use the public key to encrypt something to you. And only you with the private key are able to decrypt this value. With a private key you can also sign. If you send the message, you can sign it with your private key. And anyone with the public key can verify that it's actually you who signed it with the public key. So it's a very elegant way to solve the key distribution problem. And there are typically two different types of algorithms that we will present or talk about today. So we have the RSA, which is, I suppose, most have heard of, and elliptical curve cryptography, which has become kind of a buzzword lately. So the RSA algorithm, it's based on the discrete logarithm problem. It's actually three problems. You have the integer factorization problem, discrete logarithm problem, and then I forgot the name of this function. It has a difficult name, Teutent function something, which is supposedly easy to compute if you have two prime numbers, and difficult to compute if you only know the product. But the basic idea is the following, and it's relatively easy to understand. If you have two very large prime numbers, you multiply them together. These prime numbers have to be more or less of equal size, you can say. And you multiply them. It's very difficult to find these two prime numbers from the product. The second thing is to then, when we encrypt, if we have a message M, we convert all messages into numbers, and we can take our message to the power of an exponent that is predefined, and we do what's called the Modulus Calculus. We divide with a remainder, you can say. It's exceptionally difficult to go the other way around. If you have that result, it's very difficult to find the original message, unless you have this secret key, D. Then you have a very simple equation that's easy to compute. If you're interested, you can study these functions and see that it actually makes sense. The RSA method has been very popular, but it has two problems. You could say major problems. It has several problems, but first, obviously, it's very, very slow. It's very difficult to find these prime numbers in a good way, and you have very large keys. And these numbers, they are not random in the sense that you can have very large keys, but it doesn't give you a lot of security strength for the bits used. If you don't know exactly how to use it, it becomes a bit of a vulnerable solution also. That's why so many talk about elliptic curve cryptography, because they believe many of these problems can be solved, and they are in many cases. But otherwise, RSA cryptography has been very successful. It has endured for a long time. Now, elliptic curve cryptography has very interesting properties. Much smaller keys and faster to compute. And it's considered also difficult. But this is also, it can be difficult to know if it's actually secure or not, because we don't have enough experience, perhaps with the mathematics, to know if there are or aren't any vulnerabilities in these. So we can say that mathematics is more unknown. Until today, it has shown to be relatively secure. But there are a lot of people also saying that there are known vulnerabilities, perhaps. Elliptic comes from the study of arc lengths of ellipses hundreds of years ago, and these equations popped up. So we don't actually work with ellipses when we do elliptic curve cryptography. It's just the name of a particular type of function. And we can say elliptic curve in the simplest forms take this form. It's a third degree curve. Y squared is equal to x cube. And then we have two coefficients, a times x plus b. Basically, this curve, the curve is defined by these two constants, a and b. And if we plot these curves graphically, you see they take different forms. Now, how can you do cryptography using these curves? So the first thing to note is that as a mathematician, if you study algebraic geometry, you can add mathematical operations on a curve. So what you do is you find a way to add points. If you have 2 points on a curve, you can find always a third point, because it's a cubic curve, you could say. And so an intersection with a line always gives 3 points if you include infinity as a point. So this is just a mathematical fact. So if you have 2 points, you find the third point on the curve. Now, if the points are like this, we consider the infinity the third point. Now, to make an addition, we say that these 3 points, if you sum them together, it should always be 0. So that's just the definition. And so the mathematicians play with this, and they find that this addition works as a normal addition. We have a negative, which is a value flipped along the x-axis. You have a 0. When you add a point with its negative, you get 0. And so this is in mathematics called a abelian variety. And so mathematics become very happy now. Now they have something to play with. You have an abelian variety, and this provides a lot of, they know they have all these theorems stating what you can do with abelian varieties. And one of these things is obviously that it extends to modulus calculation in what's called finite fields and cryptography. Now, to calculate the third points is relatively easy. So if you know basic geometry, you can just draw this line, put up the equations, and you'll find a way to compute the third point. Now, you will notice that there is a difference between adding 2 distinct points with adding a point to itself. So if you add 2 points and these 2 points get closer and closer and closer, when they are the same, the sum of itself should be calculated using the tangent of the curve. Now, you get somewhat different equation for the doubling of a point. Now, this fact is used to crack elliptic curves. I'll talk more about this later. But you can have very sophisticated measurements of what the computer does, for instance, measuring what the CPU does or how much power it performs. And you can learn if it's doubling a point or if it's adding 2 different points. And from that, they can figure out what the private key is, just by monitoring. They don't even have to connect the computer. You can monitor remotely. So algorithms implementing elliptic curve cryptography, they have to take this into consideration. So it's just to show how intelligent those that want to break ciphers are. So it's very difficult sometimes to know how secure a particular cipher is. So that's the basically elliptic curve cryptography. To define an elliptic curve, you define a prime number. You take this curve, which is typically in two-dimensional space, but this time you do it in modulus this prime number. Now, if you have the integers modulus a prime number, in mathematics it becomes a field. It's what's called a finite field, and so mathematicians know that, oh, all these things continue to work, and they become very happy. But basically, this is what's done. You choose a prime number, you choose A and B, obviously. You choose any point, or a point, a generator point. And then you compute the order of this point. And what does that mean? How many times can you add this point to itself until you get to 0? Mathematicians know that you will get to 0. The question is, how many times do you have to add this? That's called the order. Typically, you want the order as big as possible. Typically, this means that the entire two-dimensional space here that's being used is every point becomes a valid point on the curve. If we look at this in 2 dimension, we saw a nice curve, but when we do modulus prime number, every point actually becomes a point on the curve if we have done this correctly. And these parameters are then published. Now, if you get these parameters, will you be able to say that this curve is a secure curve or not? I would say no, because it's very difficult to know if a curve is secure or not. Just because it's an elliptic curve doesn't mean it's secure. There are very many unsecure elliptic curves. And so there is a very famous professor in security cryptography called Bernstein. Thanks to him, actually, cryptography is allowed for private use, because he was dragged to court and was able to protect his right of free speech in the United States to do cryptography. Before that, it was illegal. But thanks to him, it has become legal to do secure cryptography in most of the Western world. And he has published on this site, Safe Curves, different tests. And he publishes different curves and shows which ones are more secure than others. He also argues that there are a lot of curves, among them those that are standardized by National Institute of Standard and Technology. They are not secure. So the most common curves, or those that are proposed, they include what's called magical constants. What's a magical constant? It's just a large constant that they have no explanation for. When you design an algorithm, all numbers have to be explained. Typically, they have to be explained as the smallest number who has this property, for instance, or something like that. It has to be explained. But there are huge magical constants in the curves provided by NIST, and funnily enough, it was the NSA who produced these constants to make the curves secure. And so there are many people who argue that these curves, these constants probably or possibly have backdoors. Oops. Television died. Sorry for that. Okay, NSA didn't like that. So you know where I live. You don't have to. Okay, we have light, at least down here. We didn't get the way. Oh, no. Okay. So. So, okay, so the NSA, their nice friends at NSA invented these magical constants with super properties that are supposed to keep us safe. And so if you want to use the cryptography and don't mind NSA knowing what you're consuming, please go ahead, use the NIST curves. If you mind, then perhaps consider another curve. And Professor Bernstein obviously publishes several curves on this site. Now, comparing elliptic curve cryptography with RSA, elliptic curve cryptography is actually much easier to understand. As long as you're fine with this inventing the plus, a new addition on curves, modulus p, if you get over that, the cryptography is much easier. You don't have to find a prime, large prime, which is difficult. You can just take any random number. Remember that n is the order of the curve, which is typically a large number. And this number is your private key. And then you take your generator point, which is public, for the curve, and you add it to itself so many times. Obviously, you don't do this linearly. You break it down by in a binary fashion. So this is why you have this doubling and addition of different points. So if you have a large number, you can shift it right, and the bit that goes out, if it's a 1, then you add. Otherwise, you just double. You know. And by scanning the power consumption of the processor, you can actually find out, unless the algorithm is cleverly designed, what the private key is. But without such methods, it's difficult to find the private key from the public key. Now, encryption. You often want to send something from Alice to Bob, or you want to agree on a shared secret or a common key. Because remember, we want to combine this with a symmetric cipher later, which is much more efficient. We want to have a method of agreeing on a shared key without actually transmitting this key, to avoid this key distribution problem. And there is this elliptic curve Diffie-Hellman algorithm, which is quite straightforward. So if Alice has her private key, Alice has a public key, which is the private key times the base point. Bob likewise has its private key and public key. Now, if Alice takes her private key and multiplies it with the public key provided by Bob, she gets the same result as if Bob takes his private key, multiplies it with the public key of Alice. Right? So that's the basic idea. They both get the same result, but the shared secret, which is the x coordinate of that point, is never transmitted. Then you apply, since these coordinates can be long, you apply a hash function to get a digest of a fixed size. And this digest you can use in your symmetric cipher. So this is actually much easier to understand than the RSA algorithm. Signatures, I will not bore you with these because they might not seem intuitive, but these steps of calculations, for instance, you do this to sign a message, and you sign it with your private key, but given the public key, there is another range of calculations you can do to verify. If you get the same result, you know it was signed with the correct private key. So this is called elliptic curve digital signatures. So these names, ECDH and ECDSA, you will see a lot if you look at ciphers used in different servers. So the key to creating a good cipher is to know how to combine different algorithms. So in communication, there is not you don't choose just one algorithm. You choose a sequence of algorithms and create a hybrid cipher. And this is where your choice of security level is important. So you choose that for my confidential information, I want 128 bits of security strength or security level. So I choose my algorithms accordingly. The asymmetric cipher helps you distribute the shared secret. It's very efficient in that regard in public environments, and the symmetric cipher is very fast when it comes to payload. So you first use the asymmetric cipher and then the symmetric. And just for your information, this is much more interesting table. So if you choose 128-bit security level, for instance, what algorithms should you use? So you can use AES 128 or together with an RSA key of 3072 bits, or a 256 to 383 bit elliptic curve. So these are all more or less the same security level, if we don't consider magical constants. Now, this is quite a lot, because there were a lot of systems only having 1,000 bits RSA keys. The Intel processor in computers were secured with 2048 bits. RSA keys up to 1500 are by many considered obsolete. And doing 2000-bit RSA keys should be avoided if you can. At least 128-bit security level for normal information that needs protection is my recommendation. If you have very sensitive information, then consider a higher security level. But don't go below 128. So these numbers, AES 128, 3072-bit RSA, or 256-bit elliptic key, a minimum. Yeah, hey, is it interesting? Anyone asleep? No? So there are other features we might want to add to our cipher. So one thing is just adding our asymmetric cipher, another our symmetric cipher. But if we want to achieve something called forward secrecy, we have to think a little bit more. What does forward secrecy mean? It means that if your private key somehow gets compromised, it can be hacked. Your computer can be hacked, someone could get your private key, or it's broken some other way. It should not compromise previous sessions. You can say your forward sessions are secured and your previous sessions are secured. In very many systems, if a key gets compromised, the entire communication history gets compromised. This is not a good properties. You want to create something called forward secrecy. Now, how do you do that? So the typical method is to make sure that every session is based on a new key. Every time you create a new session, you should be forced to generate a new key. If you generate a new private and public key and then use the elliptic curve Diffie-Hellman to derive a new shared secret that you use only for that session, any compromise of the private key in that will not compromise previous sessions because it used a different set of keys, right? And so you might see the elliptic curve Diffie-Hellman E, ephemeral, being mentioned. Ephemeral meaning short-lived or temporary. This means that the keys are generated for that particular purpose of communication, for instance. Then we get something called forward secrecy. It's a nice property. Another property, which some may require, others not, is called deniability. Now, if you send encrypted and an authenticated message to someone else, they can obviously, they use this authentication, this signature, to make sure it's you who send the message. So no one can inject the false message. But the same signature can obviously be used by others to prove that it is you who sent the message. Now, obviously, deniability is very desirable by criminals or terrorists who want to send something and then be able to deny it in case it gets cracked. But there might be other cases where deniability is important, like for dissidents in oppressed countries, for instance. Now, there is a method called off-the-record messaging. They brought this up to public awareness. And what they do is they do a counterintuitive, they publish the secret keys used for authentication. So they have two private keys, you can say, simply put. And the private key used for authentication is published afterwards. So after the receiver has authenticated the sender publishes the private key, and then the sender can claim that anyone can create that authentication because the private key is public. You get the point? So if you publish your private key that you use to sign a message after the intended recipient has authenticated it, others can claim they are you. But it doesn't matter because the intended recipient already knows, has got the message. So this is another property, deniability, that might be of interest, especially if you do software that protect the rights of people, for instance. Any questions so far before we continue? This was the basics, the different algorithms. No? Someone got mail? If not, let's continue. So now we get to points where most should be familiar, at least, because we work, most of us, with TLS or HTTPS or similar protocols. These protocols embed the choice of ciphers used to encrypt and decrypt. Normally, we don't have to select that when we use TLS. But when we design our own software with our own protocols or own data management or storage, we need to know about the ciphers directly. And we also need to know about the ciphers in order to be able to assert that TLS has sufficient security level. Now, TLS is, you can call a negotiation protocol. It negotiates ciphers, algorithms, to be used between two endpoints. There is a TCP variant called just TLS, Transport Layer Security. There is a version for UDP called, is it Datagram TLS or Distributed TLS? Datagram TLS, I guess. The most recent version is 1.3. It was released just recently. You might have seen any notices about this. The previous one was 1.2. They are riddled with vulnerabilities. And so most security experts, they try to configure servers to make sure only secure options are available. And the point of making 1.3 was not only to enhance performance, reducing time to negotiate, but also to remove vulnerable options. There are still software using older SSL, which is completely obsoleted and vulnerable. And so this is just a simple example. What TLS does is the client, in this case, connects to a server. and you have a TCP connection, and then you have a TLS handshake. This can be in the beginning, or it can be negotiated later, depending on the protocol. And here, basically, the client and server, they greet each other, exchange keys or certificates, and when they agree on the set of ciphers to use, they are finished, and then the other protocol can continue. You have bidirectional communication. DTLS works in a similar manner, but it introduces more messages because UDP is a bit different. TCP, as you might know, you have a guarantee that data you send are received in the same order. You don't have that in UDP. So you have to introduce ordering, you have to introduce some other handshaking in the beginning to make TLS work over UDP. But it's also a nice protocol. You might know about mutual TLS. Some claim mutual TLS is very secure. They use it as an argument. When you encounter these names, you have to know what is being intended to analyze, be able to know if it's done in a correct way or not. So TLS is not more secure than your use of it. So remember that. So when you connect to a server, how do you connect to a server? You typically use a domain name, right? You look up a domain name, get an IP address, you connect to that server, you get the certificate back. This certificate you validate, and in it contains the name of the domain, and you compare this name or alternative names to the name you originally used when you connected, right? So you have an out-of-band validation that you actually are talking to the right server. No such canonical validation exists for clients. So when the server gets a certificate from the client, it doesn't say anything to the server. It just has to assume that the certificate is correct if it validates. So you need to protect what I'm saying. You need to make sure the validation of certificates and endpoints is done correctly. An alternative to mutual TLS is called dial back. Then the server actually connects back to the client in a second connection to make sure that the domain names actually correspond. Now, how do you know what security level your TLS connection has? So TLS makes encryption very easy, but it also makes it difficult for a normal person to know what security level is used. And the benefit of having this loosely coupled architecture is obviously that over time, as ciphers become obsoleted, they can automatically change to newer, more secure ciphers without changing the application. So this is a very nice feature. The problem is, well, you don't know how secure it is actually, this choice. But there are tools here. I provide some links. SSL Labs is a very good site where you can actually check the security level of your server, for instance. And it will also suggest if you use weak ciphers. And it might look like this. So it analyzes your connection to your server, and you get a lot of... Have you seen these names before? You have seen similar names, right? Now you should be able to decode these names. So if we take here it says TLS ECDHE, Elliptic Curve Diffie-Hellman Ephemeral Key Change. RSA we know with AES 128 and cipher blockchaining, SHA1 hash. And here it says also it's the X25519 curve, which happens to be Bernstein's curve. So we know that, and it also says it's equal to 3072 bits RSA. Now we know, we have seen these boring slides, we know this is 128-bit security level. Okay, so it's okay. These are weak. So as an administrator, you should, unless you really need them, you should remove them. So, because if you leave weak ciphers, even if you use a secure one, someone might do what's called a downgrade attack, and use a weaker cipher and use it to derive secrets from the server. So unless you have a requirement, you should always remove weak ciphers from your server. And if you're forced to use them, separate them from other servers, for instance, or clients, so you don't lose as much when they're hacked. Yeah? Questions there? Now, public key infrastructure. You've heard of PKI, public key infrastructure. Certificates, anyone? Certificates have been around a long time. Now, the RSA company created a lot of standards. We all know about the RSA encryption algorithm, but they also did a lot of standards called the public key standards, or public key infrastructure standard. Or public key cryptography standard, sorry. And in it, they created what's called certificates. Certificates are containers of primitives, of algorithms and data in a way that's supposed to be portable. I believe when people say it's one of the more complicated internet standards available, they are not read in a day, let's say it like that. They're a bit, there are a lot of cross references. But what they do is they define an infrastructure where issuers, certificate authorities, issue certificates where they guarantee, for instance, or they have claims, for instance, a domain name, common name, or alternative names if they have multiple domain names. And they use their private key to sign this information and generate this certificate with public keys, etc. And these certificates can be sent in. They can be sent in over the web or in mail or wherever. So it's a standard data type, you can say. And issuers are ordered until you get what's called a root certificate authority. Any certificate authority with no other parent certificate authority is called a root. Now, a root certificate must be installed in your operating system. So when you validate a certificate, you get a certificate from someone you want to validate it. You first validate it cryptographically. Well, you know what I mean. Using this validation feature in the cipher. But then you also connect to the certificate authority to make sure the certificate has not been revoked. You have a revocation feature. So if a certificate gets compromised, you can revoke it with the issuer, and so even if someone uses it, even if the certificate is valid cryptographically, okay, thank you, it can still be revoked. But the root certificate cannot be checked this way, obviously, because who do you call? Ghostbusters. So it has to be installed as a secure certificate in the operating system. Now, this creates a big can of worms, because obviously, if this certificate gets compromised, anyone can use it to generate other certificates that also look valid. And if you have this installed in your operating system, then your entire system is compromised. All your applications will validate these invalid certificates. So never install certificates. And if you do anyway, you have to make sure they are always updated and maintained. You cannot leave systems with unmaintained root certificates installed. So certificates, well, they are a good idea, but unfortunately, many find them complicated to use. So So there are a lot of systems. I've seen a lot of systems using supposedly certificates to secure them that actually create more vulnerabilities than intended. And so often engineers create self-signed certificates. Anyone has created self-signed certificates? Yeah. So for the camera, there are a lot of embarrassment here. So so self-signed certificates makes your application apparently work, but it makes sure that your application doesn't validate certificates also. Because to get the self-signed certificate to work, you either have to install it, which is not good, or ignore validating it. And it's not good either. So you create a lot of vulnerabilities and holes that are not apparent. When you go into production, you remove your self-signed certificate and use a real certificate, you still have all these holes in your code because you never worked with true certificates from the beginning. So don't use self-signed certificates. There is no need anymore. 10 years ago, there was a need because they cost money and they were complicated to do. But today, we have good methods to create them securely and freely. And also, if you install a certificate, because you have to, some manufacturer gives you a certificate, you have to install it, it has to be monitored and updated properly. Because any certificate that's created from that certificate also becomes valid. And so anyone can claim to be anyone. Now, the public key cryptography standards, as I mentioned, it's just a mess of different standards, all in a big group. You might have seen all these names. They confuse a lot of people. Don't worry. We are all confused when it comes to these standards. Different file formats for certificates, and they don't work in some systems and others. And the reason why they work poorly is because the standards are very complicated to implement in a secure manner. But it might be good to know anyway. However, recent developments, if you're familiar with the automated certificate management environment, ACME, using certificates has become much easier. So before you had to create your own servers or certificate authorities to generate certificates. It was complicated, or you had to buy them. Today, you get them all for free, and you can automate it. So this is a new protocol. I believe it's in the 13th generation now, but it's quite stable. Let's Encrypt is an organization funded by most of the major players in the industry. And you have two endpoints, and you can request certificates from there in a secure manner. You get valid certificates that are accepted by all operating systems. So if you go to your favorite sites, check certificate, most probably you will find Let's Encrypt. That's because it's very easy to automate. These certificates are short-lived. Earlier certificates are long-lived, so they were valid a year or 2 years, some even longer. These certificates are short-lived, 3 months or 90 days. But since they're free to generate, you update them frequently. So that's also a good feature. There are both command line tools, multiple, and libraries in any language you like. So a friend of mine tried to introduce this in a company, and she said, you only need a line of code to get this to work, and they were very skeptical, and I tried it out. This was how I learned about it. And for me, it was actually 2 lines of code, so she was wrong, but not much. It took about 15 minutes also. But today you do it actually in 1 line. With 1 command line, you can generate it very, very easy once you've learned it, and it's not that complicated. So if you publish things on the web or somewhere else and need certificates and use self-signed certificates, stop and go to ACME. Good plastic certificates. So I want to round this talk off. You can of course come with any type of questions by presenting some forms of attack. Of course, this cannot be a complete list because we would stand here for days. There are more forms of attack than there are ciphers. Yes. Wait. You will have the honor of.
I think I can.
Wait. It's for the recording.
Hi. Okay. Perfect. Before you go into the form of attacks, for instance, typical SSH connections. Normally, which type of connections they use? Because normally you see on the tags, but I have used several servers, and some of them actually you don't see clearly. Can you do you have some?
So my recommendation is that you, if you want to know for real, you can use Wireshark, and there you can see the negotiation. It will indicate you what ciphers are being used. But typically, as you mentioned, security is completely invisible often. And so it's very difficult, and this is why so many systems are vulnerable, because it's not visible and people don't care. So if it's not visible, it doesn't exist. So unfortunately, that's the only answer I can give.
Or thank you.
More questions?
No, thank you.
Okay. Thanks. Oops. Today's technology. Okay. Yeah, I'm supposed to know how this works. I've done this now several times, but it's the age, I guess. Yeah, in my time, we didn't use this technology. We used pen and paper. No. Well, even though many of these technologies and algorithms, they might sound impressive, they are sometimes relatively easy to break, much easier to break than we perhaps first assume. Very many engineers assume hashes are irreversible. You cannot reverse them easily. And that's not true. So even though if you see a hash, it might be difficult to compute an inverse just by itself, if you know somewhat about the data on which the hash was being calculated, it's much easier. Say, for instance, if you know the hash is the personal number of a person, perhaps with the name, all you need is a dictionary of all names and all personal numbers. You compute the hashes on them, and then you compare to which hash you find. If you know it's a password, you might create what's called a rainbow table. You might figure out that most passwords only uses certain types of characters and are only certain number of characters long. Then it's often possible to create a rainbow table that will find the password from the hash. And what's a rainbow table? A rainbow table means that, okay, you have a hash. From the hash, you can compute, you can create some kind of reverse function. It takes the hash and creates a new password in the space of possible passwords. Then it computes the hash on that password and reverses it and computes a new hash and reverses it. And it does this a lot of times, a predefined number of times, 1 million or several million, whatever. And the last hash, it stores in a table together with the first password. And then it computes this for the entire password space. It becomes a big table, obviously. However, now the hacker goes into the internet and finds a hash and figures, this hash might be a password. So it looks in this rainbow table, can I find the hash? No. Okay, I reverse it, compute a new hash. Can I find this in the table? No. And I do this millions of times perhaps, until I find a hash that's actually in the table. But then I know the first password to use to create this sequence. So I take this password and start computing the hashes again until I get the hash that I actually found. And then I know the password before it is the password that will work. So rainbow tables is one method to break hashes. So never believe a hash in by itself is non-reversible. Obviously, you have heard of man-in-the-middle attacks. Very common. It's because we don't properly authenticate endpoints. We don't, as a client, properly authenticate the server, and the server doesn't properly authenticate the client, that a third party can inject itself in between and pretend to be the server. It fools the client into providing some form of credentials that it can use then to log into the server itself and act as the client. And so here you need to make sure to avoid this, to properly authenticate both clients and servers. One proper method here, or often used method, is a downgrade attack. This is why you should always remove unsecure options, because this man in the middle will offer methods to connect that are less secure than optimal. And so when using these methods, they can use vulnerabilities to find credentials, for instance. But some say that side channel attacks is the type of attack that are most reported today, and they're very ingenious. I'm sure you have read several published attacks and exploits that can be used in the cloud that use vulnerabilities, for instance, in how a modern processor works. So, for instance, a modern processor has internal cache memory, and since your cloud service, you don't control on what processor it runs, you don't control what other applications run on the same processor. And so an attacker can inject a code in the cloud, in the same provider as yours. And this code can extract the memory of the cache. And knowing SSH or knowing the structure of the different servers used, they can search for patterns in this memory and find sensitive information such as private keys. There are a lot of other interesting side channel attacks, such as I mentioned before, that you can measure the power consumption in a processor and figure out, if you know the algorithm that runs, you can figure out what it does. For instance, when you do this elliptic curve cryptography, if you don't hide, if you do a doubling or an addition, you should always do both. Then you can monitor the power consumption and find out the private key. You don't even have to connect yourself to the computer. You can actually do it just by measuring the radio waves. Timing attacks is another attack. It also works in the cloud. You can execute code on a processor and figure out from the time it takes to execute what other processes are doing on the processor. And also, obviously, you think you delete data when you delete something, but it might be deleted from the digital world, but in the analog world you have still residues called remnants, which obviously a skilled expert can utilize. So as we saw examples of earlier here, when they don't like what you're talking about, they know what you're talking about. Make sure of that. Cryptography should be done with paranoia, some say. So the more paranoid you are, the better security expert. unfortunately, that's the case. It's not only a joke. There are very many interested parties who want to know what's happening, and most of them are automatic. So if you, for instance, if you publish a server or a node on the internet, and you start to monitor what happens, it just takes minutes often for the server to be found. And then you can start, the number of intrusion attempts just grows, and within a day, not only do you have crawlers, it's very easy to separate crawlers from illicit connections, because crawlers often identify themselves. But there are a lot of interest from countries like Korea and other countries that want to know what you do, and they start automatically trying to find vulnerabilities. You can see from their patterns what vulnerabilities they are looking for. So it's not typically a human hacker. A human hacker scours the entire internet in a matter of minutes, and automatically tries to find passwords, for instance, that work. So you should upgrade your 1, 2, 3, 4 passwords to 1, 2, 3, 4, 5, 6. So to add two characters of security. Now, I mentioned before, is it legal? This was not self-evident earlier. You were actually threatened with prison if you did encryption. Thanks to Bernstein, it is legal for purely civil use in the Western world. The problem is, of course, that there exists something called dual use. So a knife can be used to cut your bread or cut your neighbor. Cutting of the bread is good, cutting of your neighbor is bad. So you need permission to cut your neighbor. That's how they reason. It's called the Vasana Agreement. It says that technology for dual use can be exported within certain countries. I've forgotten how many there are, about 40, 50 countries. But outside of that, there might be export controls, restrictions. So anything that's close to being secure needs probably permission from a government authority before you can sell it to a country outside of the Vasana Agreement list. Obviously, you need permission to sell it to a military agency, and not only by them, but from the same agency, I guess. Now, an organization called the EFF, Electronic Frontier Foundation, they're very active in protecting the rights of encryption and privacy, and they also helped Bernstein and win their case. You can read more about export controls on their site. Another question people often ask about when we talk about encryption is quantum computing. I haven't talked a lot more than saying that some algorithms are already being measured or protected for quantum computing. And there are also standards now being published that are supposedly quantum secure. And how do you know that if there is no quantum computer to run it on? Well, just as we have Turing machines to do proofs for normal algorithms, you have a quantum Turing machine for quantum algorithms. And so scientists, again, mathematicians, get very happy when they have things they can prove in theory. They sit there with algorithms they have designed. They have already got algorithms that break some of these mathematical problems. And they have proven how difficult they are, and proven that other algorithms are secure. So there are some who are actually quite prepared. Supposedly IBM has a 20-qubit machine, but to my knowledge there is not a single quantum machine that produces any output faster than normal servers. So it's difficult to know if it's a simulated quantum machine or an actual quantum machine. So there are people who are skeptical about that. And as mentioned earlier, even though this was separated from the earlier lecture, this lecture is a part of a series of Smart City lectures. It's the 5th of 8. We have the next lecture next week, Earning by Sharing in the Smart City, and we have 2 more lectures where the dates have not been set yet. But I'll publish the dates, and if you're interested, you're always welcome. We also have the Smart City labs. The last lab was yesterday, where we experiment with the things that we talk about in these lectures, and next lab next week. And so you're also obviously welcome. And many of these things that we discuss are also available in my book, Mastering Internet of Things. So you can learn more there. And I'll also make sure you have the slides available, so you can get all the links and information. So now I leave the floor to you if you have any questions or worries or problems, except personal problems perhaps. No? Well, you think about something to ask. I'll try to figure out how to put this on. No, not yet. You have to ask at least a question. No? See who's first, me or you? Who has a question? No one? Clear as mud?
You think that is still very, very early, theoretically, there's no machines out there that we can validate?
Got it working.
So there are no quantum machines that you think can be validated yet?
So there are a lot of there are companies who claim to have quantum machines, and they have APIs on the internet where you can test run your quantum algorithms. None produce a response quicker than a normal server would. Of course, there is an interest, obviously, to get funding, and quantum computing is a big buzzword. So there are a lot of people who are skeptical about these claims, since they haven't seen anything that cannot be done with conventional methods. They simply believe it's a hoax, but who knows? So if you know a quantum machine there, I can come and have a look, and I can tell you.
Aren't they trying to build one in Gothenburg? Isn't there
I don't know. Anyone else? No? You're all satisfied? You want more coffee? Okay. And I want to say thank you for coming, and hope to see you again. Okay.